checking problem 3 from the practice exam 2. So this is asking us to find the total force exerted on this dam, the given dimensions. So we want to use this force equation for hydrostatic force. So we have the density, gravity, h of y. So what we want to kind of realize here is, for convention, we're going to say that y is increasing as it goes down. So h of y is just the height, and we mark this as y equals 0 right here, so increasing y goes down to 30. Okay, so we've got h of y then is just going to be y, the distance from the top of the dam down to this representative rectangle that we have drawn here. Okay, so h of y is y. And we've got rho and g from the problem, 1,000 kilograms per cubic meter, 9.8 meters per second squared. So L of y is what we have left to do. So let's find that. Again, since we know that this dam has straight sides, L of y is going to be a linear function. So I can say it's my plus b. We've got a couple of points that we can use for this particular function. We know that when y is equal to 0, we've got the length being 100 meters. And we've also got when L is equal to 30, we know that the width of this thing is 60. Okay, so we can use that information to figure out the slope of this linear function. So again, slope for this particular case, we'll take, it's going to be L2 minus L1, so L2 minus L1, 60 minus 100, divided by 30 minus 0. Okay, so that's going to be negative 40 over 30, so negative 4/3. Okay, so the equation of our function here, the L of y is equal to negative 4/3 y, and then we have to have our plus b, but b is just the output value when y is 0, so that's 100. And again, you can just check to verify that this function is going to produce the output values that we want, as in when y is 0, you've got L being 100, and when y is 30, if you plug 30 in there, the 3 and the 30 will cancel, you get 10. So that'll be negative 40 plus 100, and that is indeed 60, so that's the function we're looking for. Okay, so the total force exerted by this dam, the total fluid force, will be the density, which is 1,000 kilograms per cubic meter, and you can check the units on this thing, times 9.8, I'm not going to write the units here, but you can verify them, 9.8 meters per second squared, so kilograms per cubic meter, meters per second squared. And then this one is going to give us h of y, that's going to be measured in meters. L of y, that's also going to be measured in meters. dy is also measured in meters. So you're going to have cubic meters here, and you can see what's going to happen with this. Should end up with newtons at the end of all of that. So anyway, the integral that we're looking for then is the starting value is going to be 0 at the top of the dam, and the last rectangle that we could draw would be at 30, so we're going to go from 0 to 30. H of y we said was y. L of y we just found, negative 4/3 y plus 100, and then dy. Okay, so if we distribute that and combine these, we're going to get 9,800 integral from 0 to 30, and we'll have negative 4/3 y squared plus 100y dy. Find the antiderivative of that, 9,800 times, let's see if I raise that to the third power, I'm going to get negative 4/9 y to the third plus 50y squared. And we're going to evaluate this between 0 and 30 again. But again, when we plug in 0, it's just going to give us 0. So really all we got to do is plug in 30 here, so let's go ahead and do that. If I plug in 30, I get, bear with me for a second, 30 cubed and 50, 30 squared. So that's 33,000, so I'm going to have 9,800 times 33,000. And that is hopefully the same answer that you see on there, 323,400,000, right? And the units on this one, newtons, since this is fluid force. Oops, I think I forgot a couple of zeros in there, 400,000. Let me fix that. Yeah, it's the answer that you see in the book anyway, or in the packet. So 323,400,000 newtons. Okay.